Hello everyone, welcome back to the mechanical vibrations tutorial. Today we are going to work on the vibration of a system under the harmonic motion of the bass. So let's begin. So as usual, we have a quick review on the system that we are going to discuss today. So today we discuss the vibration under the harmonic motion of the bass. So imagine we have a mass spring system and also damping as well. So we have M and we have a spring K and there is a damping in the system. So in the previous cases we had a force applied to the system, but today we have a case that the system is under bass motion. So imagine the base of the system has a motion like Y, and Y is harmonic. The reason that we selected harmonic is because it's like a force, a harmonic force, and in many problems in applications the force can be represented as a combination of harmonic terms. So that's why it's very important to consider it as a harmonic motion. So imagine Y is, let's say for example, capital Y as an amplitude and sine omega t. So in this case we have a bass motion. Some of the examples are, say for example, when the vibration is coming from a structure and another system is attached to that structure, or when the road is bumpy and there is a source of vibration from the bass. So it is a very important case. So the equation of motion for such systems is basically can be represented as m x double dot plus c x dot minus y dot plus k x minus y, where y is basically the bass motion, equal to 0. And then we can take out y dot and y from the left hand side and put it in the right hand side, and then use y and y dot here. Y is a sine function, so we can simply find the derivative, which is y dot. So basically we can write m x double dot plus cx dot plus kx is equal to k y sine omega t plus c omega y cos omega t. So in fact this term is from the derivative of y, and that's why we have an omega, and omega is basically the frequency of the bass motion. So imagine y is something like this. So this mimics, say for example, a bumpy road or a structure or a bridge vibration, anything that causes a vibration as a bass for our targeted system. Okay, so as you see, it's just the cos and sine function. We can combine them and we can basically set it equal to, say for example, a sine omega t minus alpha, and a and alpha could be simply found from some trigonometry. For example, I can simply write it down in here, what is a and what is basically alpha. So a is y, the amplitude, k squared plus c omega squared, and alpha is basically equal to the tan inverse of minus c omega over k. So basically, if you know the trigonometry, you can simply combine the two terms on the right hand side. So the system becomes as m x double dot plus c x dot plus kx equal to a sine omega t minus alpha. So as you see, it's very similar to the case that we have a force excitation and we can treat the system as before, but for this case we focus on the particular solution or the steady state, because it's more important. As you remember from previous tutorial, when we have a damping in the system, the transient response will go away after a while, and the remaining system or response is the steady state. So our focus would be on the private solution or particular solution or the steady state response of the system, which is xp, which is equal to x sine omega t minus phi. So this is the steady state response of the system. That's what we care actually in the vibration problems, and we can simply find x and phi same as what we did before. So for example, phi for this system is equal to the tan inverse of mc omega cube divided by k times k minus m omega squared plus c omega squared. So a little bit lengthy, and as you see, it's a bit different from the phi we had for the force vibration, and the reason is we have a different, force on the right hand side, which is different from which is coming actually from the base motion, right? We can even represent it based on zeta and r. So basically you can find it based on zeta and r as well. So but one thing that is very important in such systems and in vibration analysis under base motion is the amplitude ratio. So the amplitude ratio is basically x over y. And what is x? X is the amplitude of your system, the system that is vibrating, and y is the amplitude of the base. So in many problems and in many design analysis, you're looking into x-y ratio, right? X over y. And what is important, it's showing how much amplitude of your base is and how much your actual system is vibrating, the amplitude, right? Because the frequency we know is following the base frequency, but the amplitude would be different. So in many calculations, we look into x over y. So for these systems, we have a expression for this ratio, which is k squared plus c omega squared divided by k minus m omega squared plus c omega squared to the power of half. Or we can also represent it as a function of zeta and r, as I mentioned, and as we had before, which is equal to 1 plus 2 zeta r squared 1 minus r squared plus 2 zeta r squared to the power of half. So in some problems you know the values of k, c and omega. In other problems you deal with zeta and r, and remember zeta is c over c critical, as you remember from before, and r is the frequency ratio, omega over the natural frequency of the system, right? I'm sure that you remember that from before. So that's why we need to know both formula, and as I said, in many examples you need to basically deal with x over y. So eventually when you have x, you can find the particular response of the system, which is basically x sine omega t minus phi, and we have phi before. So keep that in mind, because you're gonna see that in the future problems. For example, the amplitude of base is given, the amplitude of the actual system is needed to be calculated, or in some cases you need to find the allowable amplitude of the base to give you a limited amount of amplitude of vibration for your main system. Okay, so there are other components for the base excitation that you need to know. For example, there is a term that is used in the vibration on the base motion, is called force transmitted. So remember that. We don't have it in today's example, but you may see it in other examples when you're dealing with different vibration problem. The force transmitted is basically the force that is transferred from the vibration system into the base. So basically, if you have this mass vibrating, there is a force which is applied to the base, right? To the base of the system. So this force is the summation of, so F is the summation of the force from the damping, which is K, from the stiffness, which is Kx minus y plus Cx dot minus y dot, which is also equal to minus mx double dot. So when you see force transmitted, it means that how much force is transmitted from the vibration system to the base, because in many design problems this is important. And there are other expressions. When you have m, when you have x double dot, you can simply find, we know already how to find x, so that x double dot is pretty easy to calculate. So we can even find the amplitude of the force transmitted in the system. So For example, in many examples, there is an expression with respect to f, the amplitude, say for example ft or something, over ky. So just some calculations to find the force transmitted into the system, right? So this is important to know. And this is our first example, but before we go to the first example, I just forgot to say something. In other sort of examples that we have, sometimes we use based on relative motion. It is pretty simple. So when we deal with relative motion, we just need to define z, a new variable, x minus y, and then our equation of motion would be different, would be m z double dot plus cz dot plus kz equal to another term which is m omega squared y sine omega t. So we basically define a relative variable z, and then we find the first derivative and the second derivative, and then we plug it into our main or original differential equation and calculate for z. We end up to this equation, which is pretty similar to the case that we have a force vibration. So if in other examples you have basically a case of relative motion, which is the relative motion between the vibrating system and the base motion, you may have other types of calculations for z amplitude or for z over y or something like that, right? So just keep it in mind. And I just want to say that because in some examples you may see that and you want to basically calculate the relative motion, right? It's pretty simple. So as I said, let's go to the first example. Let's go over the problem statement and see how we can basically calculate some of the components of the system under base motion. So basically in this system we have a landing gear, which is basically here, and I'm sure you're familiar with this word if you are familiar with airplane. So the plane is placed on a landing gear, which is simplified as a sort of spring mass damper system shown here. And then so basically m is the mass of the spring, the mass of the plane, and we have k and c, the components of the landing gear. In practice, the landing gear is more complicated, but in a 2D view and a simplified assumptions, we can take it as a mass spring system or mass spring damping system, where the mass is the airplane mass. So as you see, the road is bumpy, or like it's called the runway. Here is following a sort of harmonic function. In here it is y naught cos omega t. So it's a design problem. We need to find the value of k and c, or the stiffness and damping constants of the landing gear, so that the amplitude of the vibration of the plane is limited to 0.1 meter. The mass of the airplane or whatever located on the landing gear is given. The amplitude of the road or the bumpy base excitation is given, as well as the frequency of that. So this is again another type of problems you may have. So it's a sort of design problem. You need to design the properties of the landing gear, like the stiffness basically and the damping constant, so that the vibration amplitude of the airplane is limited to 0.1 meter. These numbers are identified based on the comfort and other components of the system. So in fact, let's rewrite what we have here. X in here is 0.1, and y naught, which is our capital Y here, is 0.2. So don't worry about the sine and cos, because like here we have a cos function, in the previous one we show sine, doesn't matter. So now we can basically use the formula we have with respect to x over y for the case that the function is based on omega, c, and k, right? We don't have to be worried about the other formula, which is based on zeta and r. We know omega here, we're looking for c and k. That's why we need to use that formula. So let's do the calculation here. So I'm gonna go to that formula and see what components we're looking for. So basically we found that x over y is equal to you can simplify it as this formula, k squared plus c omega squared divided by k minus m omega squared plus c omega squared, the whole thing to the power of half. So we can further simplify it. We can even write basically we know x and y in here in the system. So let's just make more calculations. So x was 0.1, y was 0.2 in the system. And then we can plug in other values in this case, which is, say for example, we have k squared plus c squared. Omega is given 157.08 squared divided by k minus the mass of the system is given 2000 kilograms, 157 basically 7.8 squared, and plus c squared times the frequency squared, 157.8 squared, and the whole thing to the power of half. Okay, so as you see, we have a pretty lengthy fraction, and we know the left hand side which is given, but the right hand side has two unknowns. So basically we ended up into one equation with two unknowns, k and c. So how can we basically find k and c? We have only one equation. So in such sort of problems that we have two unknowns as our design components and we only have one equation, one way is to go back to our data sheets and select one of the numbers that is basically more logical for the system, and then plug it into the equation we have and find the other variable. So this is just a one equation, two variable case, or two unknowns. So one suggestion is to select one number, do the calculation, and find the other one. This is actually one of the methods that is commonly used in vibration problems. So we do the same procedure based on the numbers we have and some of the references. We can select k here as a a reasonable number. For example, I select k equal to 5 times 10 to the power of 6 Newton per meter, right? So for such systems we need a pretty strong spring. That's why the stiffness is selected as this number. So we just need to plug in the numbers into that equation. So we have x over y was 0.1 divided by 0.2, which is half, is equal to, and the lengthy problem, we just need to plug in k into the previous case. So we have basically, let's say 25 times 10 to the power of 12 plus 2.46. These are just calculations, and I'm sure you can do it even better than me. To the power of 10 to the power of 4, or times c squared. We don't actually need this bracket, so I'm just gonna delete them all. So times 10 to the power of 4 times c squared, and in denominator we have 1966.7717 times 10 to the power of 12 plus 2.467 4 times 10 to the power of 4 times c squared, and the whole thing to the power of half. So this is just calculation, and I'm sure you can do that. So now we have only one unknown, which is c. You can do the cross multiplication and do further simplification here, and you can find basically c as equal to 1.158805 Newton seconds per meter. So the rest of it is just calculation. So we selected one number like as a reasonable value, and then we found the other one. So we can play around this. If the number you get for c is not practical, or if you have some data sheets knowing that c should be limited to a specific number, we can go back and or specific range for C, we can go back and adjust K for that. Okay, so that's the first example, and now we can move to the other one. So this is another example of a base motion. We have a grinding machine placed on a floor, and there is an isolator in the system. The isolator is basically a combination of a spring and damping in the system, but the base of this system, or basically the floor, is moving harmonically for some reason. Or so imagine like the floor is affected by a motion of another machine, which causes vibration, right? This is pretty common in industrial levels, that there is another machine which causes vibration for the floor, and the floor also is a place for another machine, or is a base for another machine. So that's why the vibration is sort of transmitted to the machine that we are analyzing, right? So I'm gonna go over the problem again. So there is a precision grinding machine shown in this picture, and the stiffness and the damping constant of the isolator is given here in this problem, is a huge number for both. And then basically we need to find the maximum acceptable displacement amplitude of the floor, which is Y here, or capital Y, so that the amplitude of the vibration of the grinding machine is restricted to a small number. Again, this is a sort of design problem. So you want to find how much vibration the system can basically undergo, so that the amplitude is limited to 10 to the power of minus 6 meter. So we need a small, for sure, we need a small, very small vibration amplitude to the grinding machine for the, for the sake of clean and nice grinding. And so we need to ensure that basically the floor is not vibrating with a huge amplitude, right? So the weight of the system is also given as 5,000 newtons. Remember, it's the weight, we have to find the mass, right? So again, we go back to our formula of X over Y. So basically, we know X here, we need to find like the max Y, or the amplitude of base or the floor, so that the X is not going beyond the number given in the problem, right? So let's do that here. Again, we go to the formula we have basically for X over Y, which is X over Y is equal to, again, we can use the K, C, omega formula. We don't need to use the zeta and R1 because we know the value of K, C, and omega. So we have X over Y equal to K squared plus C squared omega squared divided by K minus M omega squared, very similar to the case we had before, to the power of half. And we know basically X, maximum value for X is given as 10 to the power of minus 6 over Y is equal to, let's just plug in some of the numbers. I know it's a huge equation, 10 to the power of 6 basically plus I think you can basically do the calculation here. So this is K squared, so it was squared, if I'm not wrong, plus basically C is 10 to the power of 3, and the frequency is given as 200 pi squared divided by 10 to the power of 6. Let me just plug in the numbers one by one. 10 to the power of 6 minus, and here for mass we need to divide the weight by 9.81 G, and times omega 200 pi squared. And remember, the frequency should be, or must be, as a radian per second unit plus 10 to the power of 3 C basically times 200 pi squared, right? And the whole thing to the power of half. So the rest of it is again calculation. So as you see into this equation, the only unknown is y, right? So we can find y by further simplification, and if we do so, we can simply find y equal to a very small number, 169.53 times 10 to the power of minus 6 meters. So for this much y, the maximum x would be 10 to the power of minus 6. So as you see, x is much smaller than y because we have a spring and damping in the system and make sure that it works as an isolator. So with this amplitude of base, we have this amplitude or x amplitude of the grinding machine. So we need to make sure basically that y wouldn't go beyond that when we have a floor vibration. For example, we can control the floor vibration by shutting down the source of vibration or reducing the source of vibration, or designing other materials or cushions for the machine. Right, so I think that's everything for today. And as I said, it's a very important case in many practical systems that you deal with the base vibration. In the future, we go for another case, which is also very important for the harmonically excited single degree of freedom systems. So I hope you enjoyed the video, and stay tuned for the next videos.